You hear the word algorithm thrown around everywhere, right? It's in our social media feeds, it's running the stock market, it's everywhere. But what if I told you that the secret to a truly great algorithm has less to do with coding and a whole lot more to do with writing? I know, it sounds weird, but it gets right to the core of what an algorithm really is. I mean, listen to this quote from MIT's Jason Koo. More writing than you will be coding. How does that even make sense? It feels totally backward. So what's he talking about? If algorithms aren't just about banging out lines of code, then what are we missing? Well, the answer is that a real algorithm isn't just some quick and dirty solution. It's actually a complete logical argument, and that argument is built on 3 pillars that take you way beyond just typing into a computer. And here they are, the big 3. First, you have to actually solve the problem. That's the coding part we all think of. But then, and this is so crucial, you have to prove that your solution is correct, always. And finally, you have to argue that your solution is efficient. Did you catch those words? Prove, argue. That's where the writing comes in. You're not just communicating with a machine anymore, you're trying to convince other human beings. Okay, so to really understand these pillars, we got to put on our computer scientist hats for just a second. It means we have to be super precise with our language. So let's nail down what a problem and an algorithm really mean in this world. So a computational problem is kind of like a map. It shows you all the possible places you could start, those are your inputs, and all the destinations that count as a win, those are your outputs. It tells you what a right answer looks like, but it gives you absolutely 0 directions on how to get there. The algorithm, on the other hand, is the recipe. It's the step-by-step, turn-by-turn GPS directions. It's the procedure that can take any valid starting point and follow a specific path to one of those correct destinations. Every single time. All right, enough theory. Let's make this stuff concrete. We're going to use a classic example to put our new 3-pillar framework to the test. It's called the birthday problem. The question sounds simple enough, right? If you get a bunch of people in a room, is it true that at least 2 of them share a birthday? Sounds easy, but let's see what it actually takes to build a formal algorithm that solves this. So here's a logical approach. We just go through the students one at a time, and we keep a list of the birthdays we've already seen. The moment we find a birthday that's already on our list, boom, we stop. If we get through everyone and there's no match, then we know the answer is none. This feels right, you know? It seems like it solves the problem. But now, we got to deal with pillar number 2. How can we be 100% sure this procedure works? I don't just mean for 10 people in a room. I mean for a class of 400 or a social network of 1 billion. We can't possibly test every scenario. We need something more powerful. We need a formal proof. And for this job, computer scientists have this amazing tool called proof by induction. It's a really clever mathematical technique for proving something is true for a potentially infinite number of cases. It's how they can be sure that a little bit of code will work on a massive, massive scale. Think of it like a massive line of dominoes. First, you prove you can knock over the very first domino. That's your base case. Then, you prove that if any given domino falls, it is guaranteed to knock over the one right after it. That's the inductive step. If you can prove both of those things are true, you've just proven the entire line of dominoes will fall, no matter how long it is. It's just beautiful, airtight logic. So we did it. We proved our algorithm is correct. We can all go home now, right? Well, not so fast. Now we slam into pillar number 3. Just because a solution works doesn't mean it's a good solution. And in the world of computer science, good almost always means fast. So how efficient is our little procedure? Now, how do we measure speed? You might think, just use a stopwatch. But that's actually a terrible idea. Why? Because a supercomputer will always crush a laptop, even if the laptop is running a much smarter algorithm. So instead, computer scientists just count the number of basic operations, or steps the algorithm takes. That way you're measuring the cleverness of the algorithm itself, not the horsepower of the machine it's running on. This whole process has a fancy name, asymptotic analysis. But the idea behind it is actually pretty simple. We don't really care about the exact number of steps for a small group of people. What we want to know is, what happens when the group gets massive? How does the workload grow as the problem gets bigger and bigger? We're looking at the big picture trend. And when we do this analysis, we get this clear ranking of algorithm speeds. You've got your absolute superstars at the top, like constant or logarithmic time. Then you have things like linear and polynomial, which are generally considered good or efficient enough for most things. But then there's a cliff. Once you hit exponential speeds, things get really slow, really, really fast. This chart says it all, doesn't it? For a big problem, a good polynomial algorithm might take a while, sure. But an exponential one, its runtime just explodes. It goes into the stratosphere. It becomes completely unusable. For any problem of serious size, an exponential algorithm is, as Jason Koo puts it, pretty much crap. So let's zoom back out. What is the big lesson here? This isn't just about birthdays or coding. It's really about a completely different way of thinking about how to solve problems. Here's the key takeaway. An algorithm isn't just a solution you stumble upon. It's a complete, intellectual package. It's a solution that you have rigorously defined, mathematically proven to be correct, and logically argued to be efficient. It is a complete argument, from start to finish. And that brings us full circle, right back to the beginning. The most important skill isn't just speaking the language of computers, it's communicating your ideas clearly and persuasively to other people. It's convincing them that your solution isn't just a good idea, but that it's provably correct and efficient. That's why you end up doing more writing than you do coding. So I'll leave you with a challenge. Think about this three-pillar mindset. Define the problem, prove the solution works, and optimize it for efficiency. What's one problem in your own daily life, whether it's how you organize your work or learn a new skill, that you could approach like a true algorithm? The answer might totally surprise you.